unbinding and our association constant, okay? Case of A is the association constant. The forward reaction is the binding forming the complex, okay? And we have a relationship here, okay? Negative RT to natural in case of A. So we can see, remember that free energy is a state variable, so we can have there's some free energy that exists for just our protein in solution. There's some free energy for our ligand in solution. As they get really, really close together, they kind of start to maybe repel each other. They don't really know if they want to bind. There's some increase in free energy, but once they actually form their complex, this would be a giant negative change in free energy upon actually binding. This is just one example drawing, okay? You could imagine that these are flipped. I mean, it doesn't always have to look this way, but this is one example. And then just recall standard state means we're talking about 1 mole of protein binding 1 mole of ligand. So then for the dissociation case, now we've written our reaction in the reverse direction where we're going from being bound to coming apart into our two free concentrations. Okay, Kd is 1 over Ka. The sign flips when we're talking about binding. We already went through the units of these. Kind of already answered this question. Why do we use dissociation constant? It's easier for us to think in molar. Okay. And so again, our change in free energy of binding will tell us something about the likelihood of the binding and the strength of that interaction. Okay? The more negative it is, we can talk about how strong that binding is. Okay, so this is a table from your textbook that has some typical strengths of different kinds of interactions. So it has an enzyme binding to ATP, and the Kd is in this millimolar to micromolar range. We have if a signaling protein binds to its target, we're in the micromolar range. As we move down, we're getting lower and lower Kds. So we have maybe a transcription factor binding to DNA with nanomolar affinity. We have some sort of drug inhibitor binding with nano or picomolar affinity. And then down at the bottom here, we have biotin binding to avidin protein. These are both derived from eggs, from the one's from the yolk and one's from the white, and I've now forgotten which is which for some reason. But they have this femtomolar affinity. It's one of the strongest known non-covalent interactions that exist. And I kept claiming I was going to do this last semester and I didn't, so I will likely do it this semester for real, which is put some question about it. Maybe even just look it up and explain what it is to me as extra credit on the homework. Because avidin and biotin is a super popular method in a ton of types of assays. So if anyone's heard of like ELISA assay or Western blotting or electrophoresis, oftentimes you want to biotinylate something so that you can then you can put a fluorescent tag on the avidin half, and you can really make sure you're tagging only exactly what you want because these two things bind to each other with such strong affinity as opposed to other things. This is a nice, I thought I had a website pop up for you to read about that, but maybe not. Okay, so the last column here is change in free energy of binding. So what do you expect these numbers to look like as you go down the table? Increase how? Increase in absolute value, but more negative. Okay? So as expected, we're going from about a negative 10 and then maybe about 10-fold difference at the bottom. So even though Kd is technically dimensionless, we're going to think about it with units of concentration, where small means tighter binding. Oh, there it is. Okay. So here we go. This is a good page that talks about the biotin-avidin relationship and using it for a lot of different applications.